In this video, we'll be going through an entire example of how to complete a one-way ANOVA from start to finish, going through each step of our hypothesis testing procedure. Let's get started. So let's look at this example. So in this example, we have a group of researchers who are studying treatments for depression, and they're comparing three groups of patients with depression. One group receives a placebo, one receives an antidepressant medication, and the third receives an antidepressant medication along with psychotherapy. And so we want to think about restating our question as a research and null hypothesis, just like always. And specifically, in this case, our null hypothesis is just a little bit different because we don't have that. We can have a very specific research hypothesis. And so particularly, let's look at this first. Our research hypothesis could be that the means differ among the different populations, or it could be that a particular set of population means differ. So I can predict if I have three groups, I can say that group 3 is going to be greater than group 1, and that can be one of my predictions. I can have a very, very specific prediction, or I can just predict one of these groups isn't going to be like the others. For the null hypothesis here, if I have this really specific hypothesis that group 3 is going to be greater than group 1 or more than group 1, then just negating that research hypothesis doesn't quite do the trick for what my null hypothesis needs to be. And so for my null hypothesis for the ANOVA, it's really that the populations being compared all have the same mean. So getting back to our example here. So in this case, we are going to look at how effective these therapies are. And so my null hypothesis is going to be that these therapies are not effective and the means are all going to be the same. There'll be no differences between my groups. And my research hypothesis can be that there are going to be a difference between this group. So particularly, I might predict that the medicine group will be greater than the placebo group, and the medicine and therapy group might be better than the medicine or the placebo group. There's lots of different hypotheses that I might have here. And so next up, we want to determine the characteristics of our comparison distribution. And for the ANOVA, again, we always ask, what is our comparison distribution? Make sure that we know what that is. And for the ANOVA, we said that it was going to be this distribution of ratios of variances. And so we need to figure out what our degrees of freedom are as part of this process. And so we're going to do this in preparation for looking up our cutoff score. And so particularly if I have 3 groups, then my DF between is going to be 3 minus 1 is 2. And remember that our degrees of freedom is n minus 1 for each group. And each of those groups had 5 people in it. So I'm going to add up 5 minus 1, 4, and then plus 4 because all of our groups were even. And again, no matter how many groups we have, we're just going to add up all of the degrees of freedom for all of those groups. And so this brings my degrees of freedom, my DF within, to 12. And so this is a little bit different, particularly for the ANOVA. It makes more sense, the way this is set up, for us to actually do the rest of our calculations really as part of our step 4 as we're determining our sample score. And so really in step 2 for the ANOVA, the only thing that I like to do is to go ahead and calculate those degrees of freedom. And then in step 4, you'll see that there'll be several calculations, much like we normally have in step 2, but it'll flow a little better if we put all of that into step 4. And so right now we're going to move to determining the cutoff score on our comparison distribution. And so particularly we said that we have 2 degrees of freedom and 12 degrees of freedom. And so 2 degrees of freedom is going to be our numerator degrees of freedom, our DF between, and 12 degrees of freedom is going to be our DF within. And so if I can find my denominator degrees of freedom, my DF within first, I'm going to go down to 12 and I'm going to start moving across here. I'm going to go to the 0.05 is what the significance level that we want. I'm going to move over to the denominator degrees of freedom. That's 2. We're going to see 12 df within, 0.05 significance level, moving over to numerator, our df between of 2. And we need an F ratio of greater than 3.89 to reject our null hypothesis. The 3.89 is going to be our cutoff score. And so now here we get to step 4. And so here we're going to determine our sample score on the comparison distribution. And again, here we'll actually need a few things this time. And so we're going to really be calculating 2 things, which will each have about 2 steps, although some of those steps might have some additional sections to them or multi-part steps here. And then we're going to calculate that F ratio. And this is really what we want, but we need to do all of this to get it. And so the first thing we're going to do is get the within groups estimate of the population variance, estimating each sample's population variance, and then using those estimates to create a type of pooled variance, although this will be a little bit different than how we did it in our prior test. And then we're going to get the between groups estimate of the population variance. And here we're going to estimate the variance of the distribution of means, and then figure the estimated variance of the population of individual scores before getting that F ratio. And so again, we have our procedure for estimating population variance. We've been practicing this all through t-tests, and so this should be really familiar. Feel free to check out one of the earlier videos on estimating population variance if you're not sure of this yet. And so this is going to be part 1 of getting that within groups estimate of the population variance. This is going to be the same way that we've been estimating population variance, our same formula, our same procedure. We're going to get our deviation scores, square those deviation scores, get the sum of the squared deviation scores, and then divide by n-1. And so for our placebo condition, this is exactly what I've done. So I got the mean of our placebo condition scores, subtracting that mean from each of our scores, square, and then add, and then divide by n-1, which is 5 minus 1 here. And here I'm going to get that our estimated population variance for the placebo group is 5.70. I'm going to do the same thing for the medicine group. I'm going to do the same thing for the medicine and therapy group. Next, I'm going to use these 3 estimated population variances that I just calculated to get the within groups estimate of the population variance. And so what I'm really doing here is just really taking an average. And so for our purposes, this is just going to be I'm adding these up and dividing by the number of groups. And again, that's our within groups estimate of the population variance. In our case, this is just going to be a straight average here. All of the examples that we'll be using will have the same number of participants in each group, so we won't need to weight these. And for the purposes of this video, we're not going to worry about cases where we might have uneven groups. And so if I do that addition, do that division, we get 6.07. Next up, I need to get my between groups estimate of the population variance. And so part 1 of this is going to be to estimate the variance of the distribution of means. And to do this, I'm going to use this formula right over here. And this should look kind of familiar. This looks kind of like what our population estimate of the population variance formula looks like, but it's a little bit different. And so specifically here, instead of x minus m, we're getting m minus gm. And in this case, this is, we want the sum of the squares of these deviation scores that are the mean minus the grand mean. And the grand mean is essentially the mean of the means. It's the mean of all of our scores, not just in one condition, but in all our conditions. So in order to do this, we need to get that grand mean. And so we can calculate that by getting the mean of all of our scores, or if we have the means for individual groups, we can get the mean of the means. And then we're going to subtract the sample means from the overall mean. And then square each of those deviation scores, add up the squared deviation scores, and divide the sum of the squared deviations by df between. And again, that's n groups minus 1. And so in order to do this, we're going to get our grand mean, which is 16.2 here. And then I'm going to subtract that from each of our sample means. And once I have those differences, I can square them and add them up. And so this section is, we're using some different numbers here, these means and the grand mean rather than our x's and our regular means. But basically this process is very, very similar to that estimated population variance. And here though, we're going to divide by df between. And we're going to get this estimated variance of the distribution of means is 5.56. And now we're going to take that number and we're going to figure out the estimated variance of the population of individual scores. And so typically we're going from the population to the distribution of means. And when we do that, we divide by n. So when we go from the distribution of means to the population, we're going to multiply by n. And so specifically, we're going to just plug in the number for that distribution of means value, multiply by n, and n here is going to be the number of scores in a single group. And remember, our groups have equal numbers of people in them each. We do that multiplication and we get 27.80. And here, this is our last step of step 4 here. And so we're going to get our F ratio, and this is our score. This is our sample score. And here we're going to compare our estimates by creating a ratio. And this ratio is going to see our between groups estimate of the population variance divided by our within groups estimate of the population variance. And I like to remember this, if you can't remember which one is which, I like to remember that the B for between is on top and the W for within is on the bottom because B comes before W in the alphabet. And remember that, or we will see here that if the null hypothesis is true, our within groups and between groups estimates should be really, really similar, and our ratio should be just around 1. If our F value is much greater than 1, it's likely that we'll be rejecting our null hypothesis. And we'll still use a table to get our cutoff scores and compare that to our F value, just like we normally do. Step 5 is always going to be the same for how we decide whether to reject or fail to reject our null hypothesis. But it's a good rule of thumb that if our F value is much greater than 1, it's pretty likely that we'll be rejecting that null hypothesis. And so if the research hypothesis is true, the between groups estimate should be larger than the within groups estimate. And that's going to allow that ratio to be greater than 1. And so we'll take our between groups estimate of our variance and our within groups estimate, plug these numbers into our formula, do that division, and here we can see that our F value is going to be 4.58. Here we can see that this value is much larger than 1, so we can maybe suspect that we might be rejecting our null hypothesis. But let's go ahead and do our final step here and decide whether we should reject that null hypothesis. And so you can see our number line here. I like to draw these out. I encourage you to do the same. And you can go ahead and draw that positively skewed F distribution if you'd like. I just have this number line here, which is also fine. I'm starting at 0 since that's how our F distribution will be. And remember that our cutoff score was 3.89 and our sample F value that we just calculated was 4.58. And so that 4.58, that sample F value is going to be more extreme, further in the tails than our cutoff score. And so we're going to reject our null hypothesis.